and the third part. Okay, so now what we're doing is we're sketching our cubic functions. Okay, but before you sketch the cubic functions, I just wanted to talk about all the theory that you have already. Okay, so with our cubic function, it's going to be looking something like this. This one here is a positive one. Okay, so I just sketched that one for now to explain to you that at this point, from this point, or from negative infinity all the way up until this particular point over here, you can see that it's increasing. Okay, at this particular point it's stationary. Today in class, when I was explaining this graph, I said think of this as a roller coaster. Okay, so you increasing, going all the way up in the roller coaster. You come to a certain point, okay, where they just pause the roller coaster for a second, then you start going all the way down. Okay, so at that point it's stationary. Okay, and if something is stationary, our gradient at this particular point, or it's going to be like this, it's a straight line like this, right? Our gradient at this particular point is going to be 0. Okay, so I've written here, and we discussed this in the previous video when we were calculating the tangent, the equation of a tangent, right? So do you see here, my first derivative is equal to 0 at this stationary point. Anyway, we're continuing down, it's decreasing. Okay, we come to another stationary point where my derivative is equal to 0, and then here we are increasing again. At the points where we're increasing, my first derivative is greater than 0. At the points where we're decreasing, my first derivative is less than 0. Okay, and that makes sense. If you remember, just grab a piece of paper. Okay, if you remember in class when we were talking about equations of all the functions that I did with you guys when we were doing extra lessons, or even when we were talking about analytical geometry, I made this sketch here for you guys. It looked like this. Okay, and we know that when we have a positive m value, it's increasing. If we have a negative m value, it's decreasing, this being m being gradient. If we have a m value of 0, it's a straight horizontal line like this. Okay, that's exactly what's happening over here. See, m value, this here is our gradient. Gradient is greater than 0, so increasing. Gradient less than 0, so decreasing. Gradient greater than 0, so increasing. It's very important to know. Okay, and then at the points, I'm repeating what I just said, at the points where it's stationary or the turning points, then our derivative is equal to 0. Okay, I'm going to recap on the concavity. This is our graph over here. This part here, it's concave down, okay, because all of the tangents are drawn at the top of it. This point over here, it's concave up because all the tangents are drawn underneath it. We got here second derivative less than 0, this side second derivative greater than 0, and then at the point where it changes from concave down to concave up, or if it was the other way around where it was concave up to concave down, it would be known as the point of inflection. At the point of inflection, our second derivative is equal to 0. Okay, now there's very important things that we need to remember when we're sketching these graphs. Okay, so when we mark in your graphs, there's 5 important things that we're looking for. One is the shape. If our a value is greater than 0, it's going to be increasing, like how I have this one over here. If my a value is less than 0, so a negative number, it's going to be decreasing. It's going to look something like this. Okay, I have another sketch for you guys to show you exactly what it looks like. Then we're going to be looking for your x-intercepts, and x-intercepts we know for all of our functions, whether it's trig functions, whether it's our normal algebraic functions like parabola, hyperbola, exponential. Okay, we know y is equal to 0 at those x-intercepts. Okay, now to calculate your x-intercept, since we're working with a cubic, remember how I taught you guys in the beginning before we started with the actual calculus, we did the factor and the remainder theorem. And then when we were busy with the factor theorem, we were actually factorizing those cubic expressions. And then we even had a couple of them where we were solving for x. Okay, that's exactly what we're going to be doing over here. Okay, so you're going to be using either long division if you're comfortable with that, or synthetic division to actually solve for those x-intercepts. Or for the students that have their silver calculators, you're going to be using that equation mode and finding your 3 x-intercepts. Okay, for y-intercept, we know that x is equal to 0, so you just sub x is 0 and solve for y, or else if it's in the form y is equal to ax cubed plus bx squared plus cx plus d, it's basically that d value. Okay, then we have to calculate, or we look for your stationary or turning points, and you have to calculate those. How do you calculate it? You will make your first derivative equal to 0. You're going to then solve for an x value. Okay, there's going to be 2 of them in most cases, because when you find the derivative of a cubic graph, it's going to give you a quadratic. Okay, so there's going to give you 2 x values. You sub those x values separately into the f of x equation, that means the original equation, and you'll find your corresponding y values. That means you can plot then this point over here and this point over here. Then we look for your point of inflection, and you have to list it for us, or write it down on the graph for us. And this here is where the second derivative is equal to 0, same like how we did over there. Equate it to 0, find the x value, and then sub in to the original equation to find our y value. Okay, I wrote it out again for you guys. Here's an example that we're going to be drawing. So here's our graph. Okay, as you can see, my x value, my a value, the value here in front of the x cubed, is a positive value. That means our graph is going to be looking like that, where it's increasing, decreasing, increasing, right? Okay, we need to find our x-intercepts. That means where y is equal to 0. So those calculations, we don't generally mark it in your people's work. Okay, what we're actually looking for is your graph, and we want to see the x-intercepts on your graph. So for this part, you can calculate it either synthetic division or long division or solve a calculator. That's perfectly fine. All right, I'm going to remind you guys, for the people that don't have the silver calculator, even though I have one over here, how do we find these answers? Okay, I'm going to start at -5 and I'm going to end at 5. Step, remember, is 1. I'm going to look for a 0 over here. There we go, I found a 0. So that means the value should be 1. When we're writing out our factor, it's x minus 1. Now I need to figure out this quadratic part over here, isn't it? So how am I going to figure that out? Synthetic division, since that's the easiest, okay? Okay, you bring down the 1, 1 multiplied by 1. Add these two. -5 multiplied by 1. Add these two. 4 multiplied by 1. Add these two. Should give you 0. That means these are the coefficients of that. Okay. Now you can factorize this either using the quadratic formula or using your grade 9 knowledge of factorization. What's this? Minus and minus. There we go. Okay, so now my x-intercepts are x equals 1, x equals 4, x equals 1. You notice there's two of them that are exactly the same, which we're going to see now. It's going to be actually one of our turning points because it's cutting there at that point and turning, and so it's cutting there basically twice. Okay, y-intercept is where x is equal to 0. You can show the whole substitution if you want to. I explained it earlier. It's basically the d value, so this here is going to be y is equal to negative 4. Okay, then to find my turning points, I said it's where my first derivative is equal to 0. So my first derivative is 3x squared minus 12x plus 9. Go back there so you know what I did. I said 3x squared minus 12x plus 9. Okay. I'm going to divide everything by 3, or you can sub the whole thing into the quadratic formula, that's fine. There we go. Didn't we say that this is going to be one of the turning points? Now we're not yet done with this. We need to find the y value, okay? So this one here, y value is equal to, and this one here, y value is equal to. Okay. So I'm going to take this 3 and I'm going to substitute it back into the original. So okay. Now we already know that this one here is going to give us 0. I'm just going to sub it in to show you guys again. There we go. Okay, important point so far. Now we need to find the point of inflection. So this here we know is the second derivative equal to 0. So we've got the first derivative here. We're going to find the second derivative. So that's going to give us 6x minus 12. Okay, and this here has to be equal to 0. Okay, we need to find the corresponding y value, so we're going to sub it into the equation. Okay, so that's where our point of inflection is. Now we need to be talking about the shape. Okay, so to work out the shape, I already mentioned to you that our shape is looking somewhat like this. Okay, but let's say we didn't know that it's looking like that. How do we determine what the shape looks like? So we're going to be doing, what is this called? I think it's called the first derivative test. Okay, so you take these 2 points over here, which is 3 and 1. Okay, we go with 1 and 3. The derivative was 3x squared. This is 3x squared minus 12x plus 9. Okay, now we know at this point over here, it gives us 0. The gradient here is 0. Okay, because it was where we made it equal to 0, the first derivative equal to 0. What we're going to do now is we're going to find a value smaller than 1, and you can pick any value smaller than 1, you're going to sub it into here and you're going to see what sign it gives us, okay? So we're not really worried about what number it gives us, we're worried about the sign. So I'm going to pick the number 0 because it's smaller than 1. You can pick any number smaller than 1. And I'm going to sub it into this equation, the derivative equation, okay? So 3 times 0. You see, it gives us something that's positive. So in this side here, we know that the gradient is positive. Okay. This side here, we're going to find a value between 1 and 3. Any value, you can use decimals, anything. Okay. I'm going to pick the most easiest one. Between 1 and 3 is 2. Sub it into this equation here. And we see that our answer is negative. So that means here it's negative. Now we're going to do the exact same thing, just this time greater than 3. So I'm going to pick the number 4. Do you see how my answer is positive? So that means my graph is looking like this. It's increasing until this point, then it's decreasing. Okay, you can go over this. Wait, let's do this again. Increasing, coming to this point, decreasing, coming to this point, increasing again. That's what my graph is going to be looking like, okay? This here is purely for yourself. No one marks this, okay? It's for yourself so that you yourself know what type of graph it's looking like, okay? And you don't have to make this drawing so big, you can make it much smaller, okay? All right, the important part is actually sketching it on a Cartesian plane. So I sketched a Cartesian plane for myself here, okay? I looked at these values over here. I have 1, 4, 1, okay? I have negative 4, I have 3 and negative 4, 1 and 0, and then the side 2 and negative 2. So it wasn't really that big numbers. So here's my Cartesian plane, and because it wasn't such big numbers, I was jumping each time with 1, 1, 1, 1, 1. Okay, and I'm going to just go ahead and plot all of these points, and then I'm going to show you how we join those, or draw the actual graph, join all of those points. Okay, it was a bit difficult to actually draw it while holding the phone in my hand, but anyway, remember we had the point 1 as our x-intercept, 4 as our x-intercept, 1 as our x-intercept. I went ahead and I plotted 1, 1, and 4. We had our y-intercept to be negative 4. That's what I did over here. Y-intercept at negative 4. Our turning points were at 3 and negative 4, and 1 and 0. So there it is. 1 and 0, it must turn, and at 3 and negative 4, it must turn. Okay, and then my point of inflection, 2 and negative 2. There we go, 2 and negative 2. And we know that our shape for this one is increasing, decreasing, increasing. So that's exactly what I did. And I just made sure that it passes through all of the points that I have. Okay, and that there is the sketching of a cubic graph. It's actually not that bad. It's easy marks if it was in your paper, okay? I'm going to try another one with you. I can find where I wrote it. There we go. Okay. Lasagna is slightly different. I've given it to you in a slightly different format. Okay. And this one here, you're going to see it even looks different from that one over there. It is still a cubic function. How do I know it's cubic? It's to the power of 3. Okay. To find my x-intercept, I need to make y equal to 0. So I'm going to say 0 equals... Okay, this here is negative 8. Dividing both sides by the negative to get rid of it over there. Okay, and I'm going to cube root this. Okay, so that means I'm going to get that's what I'm doing over there. Okay, for this one here, when you cube root in something, you don't have to worry like when you square root in something that there's two possible solutions. Yes, technically there are three different solutions. It just so happens that because it's positive over here, all three of our solutions are all positive too. Okay, if this was negative over here and you cube rooted it, all three of your solutions would have been negative too. Okay, so this here we're going to get 2 minus 1 equals to x, so our x-intercept is basically at 1. That's where our x-intercept is. Okay, now you're confused because didn't I say that if it's cubic, we're going to have 3 x-intercepts? Okay, bear with me. You're going to see what's happening with this particular one, okay? This y-intercept is where x is equal to 0. So we're going to say y equals negative 0 plus 1. Okay, and this here, if we calculate it, we get y is equal to 7 because negative 1 to the power of 3 is 1 and there's a negative in front of it, so negative 1 plus 8 gives me the 7. Okay, now I need to determine my stationary points. Okay, in order to determine my stationary points, I need to find my first derivative. But since it's in this format over here, I'm going to have to open this up. Okay, so multiply out, and then I'm going to find the derivative. Okay, now you can use Pascal's triangle for this part over here, or you can just actually multiply the whole thing out. Okay, so I actually worked it out on the side. That's where I'm copying it from. It's basically multiplying this whole thing out. That's what we're doing, okay? That's what the equation would look like, okay? Now to find its stationary points, we're going to find the first derivative, and we're going to make it equal to 0. So our first derivative is going to be negative 3x squared I'm going to divide everything by negative 3. And then I'm going to find the factors of this. Okay, I need to find my actual y values for each of this. They're the exact same number. So that means I'm going to sub into the original equation. So you can choose to sub into there, or you can choose to sub into this one. Okay. So this point here is 8. This point here is basically 8. Okay. Now I need to find my point of inflection. We know point of inflection, second derivative equal to 0. My first derivative was this value here. This expression, this part of it here. So my second derivative is going to be okay. This is going to give me and if we substitute this into the equation, the original equation, we're going to end up with y is equal to 8. Quite a bit of repetition of points. Okay, let's quickly talk about the shape. Since I only have one particular, turning point or stationary point, Plot that over there. We're going to substitute a value less than it and greater than it into the derivative and see what our signs are going to look like. Okay, so this is going to be okay. Oh, sorry, this should have been smaller. It gives us negative. So on this side here, it's negative. That means decreasing. A number bigger, so I'm going to go with 2. It gives us negative again. Okay, quite interesting. So how are we going to be plotting our curve? Okay, this is what it's going to look like. Where is it at? Okay, our points were point of inflection. Wait, let's go back. Our points that were important: x-intercept at 1, y-intercept at 7, -1 and 8, -1 and 8. Let's plot those points, and then I'm going to show you what the curve looks like. Okay, I went ahead and plotted them. My graph looks a bit weird because of my axis. I was running out of space as you seen earlier, so I jumped each time by 2. I didn't realize that, oh crap, our values here are at 8. So I jumped each time by 2, making my y-axis all 2s, and my x-axis was fine. I was jumping in 1s. My x-intercept was here at 1. My y-intercept is here at 7. My point of inflection and my turning point is here at -1 and 8. And then remember, it said that it was decreasing, coming to the turning point and then decreasing again, which is exactly what's happening over here. This is a cubic graph. Decreasing, comes to the point of inflection, decreasing. Okay, and there we go. That's our cubic graph. Okay, quick summary on everything that you should know about these cubic graphs so that it makes it easier for you to draw. If our a value is greater than 0, then it looks like this: increasing, decreasing, increasing. Or else if it was like this weird one that we had over here, then it would look something like this. Increasing, comes to that turning point and the point of inflection, and then increasing again, right? Or else if our a value is less than 0, meaning it's reflected along the x-axis, then we have something like this: decreasing, increasing, decreasing. Or else like how we had this weird one over here, where it was just decreasing, comes to the point of inflection and turning point, and then decreasing. All right, another type of question that you're going to get asked is determine the local maximum, or else determine the local minimum, right? Now, if you look at these graphs, can you see that this graph is continuing all the way down, okay? And it's increasing all the way up. So that means technically our range for this over here, and same thing over here, increasing all the way up, decreasing all the way down. Our range for this over here is basically y is an element of real numbers. So how on earth can I have a maximum or a minimum, right? We have something called the local maximum and the local minimum. And that's what I've written over here for you. This point over here, the turning point here is the local maximum. The turning point here would be the local minimum. In this one over here, local minimum, local maximum. Now how are you going to figure this out? Set a first derivative equal to 0. You're going to get 2 possible x values. And then you just need to see whether it's an increasing, decreasing, increasing. Then the lesser one of the 2 x values that you're going to get is going to be the maximum, and the higher of the 2 x values that you would have worked out when you found the first derivative equal to 0 would be the local minimum. Or when you sketch it, you can see which one is local maximum and local minimum, and vice versa if it was a decreasing, increasing, decreasing graph. All right, another thing that you need to know with your cubic graph and its derivatives. Okay, so if I have a cubic graph, I've labeled this local maximum as A, local minimum here as C, right? It is our turning points, and I've labeled here B. It's not the x-intercept, it's actually the point of inflection. There it is over here. if I found the derivative of a cubic graph, it basically gives me something to the power of 2. And anything to the power of 2 is basically a parabola. So this is what my parabola looks like. It's important to note that this a value, whatever the local maximum, the turning point value here of the cubic graph was, it becomes the x-intercept of my parabola. And this value over here becomes the other x-intercept of my parabola. This point of inflection here becomes the turning point of my parabola. I've written it down over here for you. And then if you find the derivative of this parabola, so that means the second derivative of this one, it becomes a straight line. And this b value over here, which was the turning point, basically becomes the x-intercept of the straight line. Okay, I've drawn it on the side over here with the ones where they decrease in. So this point over here is A, this point here is B, this point is C. So this A value over here becomes the x-intercept here. The C value, whatever the x-coordinate at that point is, becomes the x-intercept over here. This B value, whatever the point of inflection was, becomes my turning point over there. And same thing, this turning point, whatever it is of the parabola, which is the first derivative, when we find the second derivative of it, becomes the x-intercept. This is very important to note, okay? They might ask you a question where they give you, for example, the parabola. They tell you that the parabola that they've sketched over there is actually the derivative of f of x. And then they ask you questions about f of x based on this one over here. Okay, so they might ask you what is the turning point, what are the x coordinates of the turning points of the original function. Now you must know that it's this and this, and that is the x-intercepts become the turning points of the function before it, the cubic function, things like that. Okay, on that note, please remember that when we're talking about parabolas, there's quite a few ways to determine the turning point, okay? Let me write this down because it's always easier when we see things. This is basically to help you find the turning point of a parabola, okay? Now, I'm just listing down all the possible ways that you can do it, okay? Option 1, the easiest. X is equal to minus b over 2a. We learned this, okay? So our equation is y is equal to ax squared plus bx plus c. I know I'm deviating slightly from calculus cubic graphs, but this is very important as well, okay? So you take your b value divided by, negative b over 2a. And then to find your y value, you would sub it back into this equation, whatever it is. That's one way of doing it. The second way of doing it is by completing the square. When you complete the square, you're going to end up in this format. Y is equal to a x minus b all squared plus q, where my p and my q are going to be the turning point. So that's the second way. The third way, if ever you need to work out the turning point, do you agree with me? Let's just sketch this to make it easier. Here's my parabola. Let's call this x1. Let's call this x2. Okay. I mentioned this in class, that this here is basically our axis of symmetry, okay? And this axis of symmetry is basically the x value at your turning point. So I'm going to call it P because that's what it is from here, right? If it's the axis of symmetry, the distance from this x-intercept till the axis of symmetry is exactly the distance from the axis of symmetry to this turning point. So one other way of calculating what this p value or this x coordinate of the turning point is you work out the distance from this point to this point and divide it by 2. You'd be able to find what the x coordinate of the turning point is. You then sub it back into the equation of the straight line of the parabola, and you'd find your y value. So that's the third way of doing it. And the fourth way that we now just learned, if you want to find a turning point, you find the derivative and equate it to 0. Once you find your derivative equated to 0, you find your x value. You then find your y value by subbing it back into the original. It's very important to note you now have 4 ways that you can calculate your turning point of a parabola. Okay, the next video is going to be on calculations where we give you the graph and you have to actually answer questions based on it. That one's very important. It also has those questions that say for which values of x is f of x times the derivative greater than 0 and stuff like that.